Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Steve Markham with us today. Hi, Steve.
Hey, how's it going?
I'm doing really well today on this fall day in Phoenix.
Nice. I'm in Crestline, California. It's a small mountain town just north of San Bernardino.
Oh.
I'm at Caltech, which is located in Pasadena. It's about an hour drive from here, but given the situation with the pandemic, it's nice to be around trees and lakes and whatnot.
Very good. Very good. Yeah. So does Caltech have any plans to open? I mean, are they doing classes, or what are they going to do in the spring, or is it all sort of TBD?
I think that it's currently TBD. I'm TAing a class right now, and it's 100% virtual. I think that the only in-person components of learning are the parts that are impossible to do virtually. For example, experimental work or lab work that you have to do for certain classes. But in general, it's the campus remains mostly closed. Although you can go, but you have to log on the internet what times you were there, so that they can contact trace just in case anyone gets sick. I think they're being pretty responsible about it.
Okay, cool. So how many astronomy books do you have over your right shoulder on that bookcase there?
Oh, not very many. A lot of my astronomy books are back at the office. Unfortunately, I'll have to transport those at some point.
Are those mainly novels then over your shoulder, or what are those?
Yeah, novels. A few. Just like I'm interested in classical history, so there are some classical history books. There's a whole shelf devoted to Harry Potter. So
cool.
That
Very
too.
Good. Awesome. Very good. Steve, what do you like to do for research?
So my focus right now is on, I mentioned I was a grad student at Caltech. I'm working with Dave Stevenson. And primarily I'm focused on two areas. One is giant planet seismology, which is going to be the topic that I'm talking about here. And I'm also interested in the dynamics of convection in hydrogen atmospheres, in particular convective inhibition and moist adiabaticity, and how it affects thermal evolution and meteorology. So I'm working on a project related to that too. So the two are tangentially related in that we think maybe an excitation mechanism for seismology might be meteorological phenomena. And so that's sort of the tenuous connection between them. Cool. Although the applications that I'm exploring right now are not entirely connected.
In time. So how far along are you in your trajectory as a grad student? When do you anticipate being Dr. Markham?
I think that it's probably, I'm starting my 5th year now, so I'd like to wrap it up in the next year. I'm on a finesse fellowship right now, and I have funding for another 2 years. So it depends on the progress of my science and whether or not I can get a job, I think.
Right. Okay. Very good. And that will bring us to this really lovely Planetary Science Journal, which, as most of you will know, this is the newest AAS Journal journal. And the nice thing about the PSJ is it's open access. So all of the articles are open access, so you can access the real article. And on this one, it is possible evidence of P modes in Cassini measurements of Saturn's gravity field. And Steve, take us away.
Yeah, I'm glad you mentioned the open access aspect. That's the reason I published it here instead of a lot of planetary science has traditionally been published in Icarus, which is not open access, but I think it's important for science to be accessible to everyone. So good reason to choose this journal. Here's a plug. Okay, so this is possible evidence of P modes in Cassini measurements of Saturn's gravity field. The reason it says possible is because what we're really doing here is we're taking one interpretation of an interesting aspect of the Cassini data, and we're exploring what its implications would be if that interpretation were indeed correct. So the thing in question is sometimes called the dark side of Cassini's gravity field, and this is because when you think about giant planets, you usually expect that because they're fluid bodies, that you can use symmetry arguments such that their gravity field should be static. It shouldn't be changing because it should be in equilibrium. It should be zonally symmetric, because if there were some asymmetry in the gravity field, then it should correct itself because it's a fluid body again, and it's rotating, so it's not necessarily going to be spherically symmetric. And it should be north-south asymmetric, because if there's some density anomaly between the north and the south, again, it's a fluid body, so the lowest energy state, it should equilibrate. However, the observations find that that is actually not the case for Saturn. And the part that is well understood is a zonally symmetric but north-south asymmetric component to the gravity field, which are the so-called odd gravity harmonics. Not because they're strange, but actually sort of because they're strange, but because they're not north-south symmetric. So that's what is meant by odd. And an additional source of currently unknown gravity perturbations. So the way these experiments are conducted is you have the spacecraft in orbit around the planet, and you measure the Doppler shift in the electromagnetic signals that you receive from the spacecraft, and that tells you the velocity of the spacecraft. And you can compare that against a model to see if there are any residual sources. So you can model what the velocity of the spacecraft should be if it were a spherically symmetric gravity field, for example. And then you can model how adding different gravity harmonics affects that, what you expect. Okay. So ordinarily, you can explain these. It was expected that you could explain the observed gravity signal using even, so north-south symmetric and zonally symmetric gravity harmonics. One interesting thing that was found in this experiment was the north-south asymmetry, which has been attributed to the zonal winds, and also that the relationship between the even gravity harmonics did not follow what you would theoretically predict if it was a rigid rotation. So this is evidence of differential rotation and the impact of the zonal winds on the gravity field. So these are important results. Yep. And I want to mention that the odd gravity harmonics and the deviation away from the rigid body rotation are of the order of millimeters per second. So this is the velocity perturbation that we're talking about. So we have exquisite accuracy. And but what we also find that was totally unexpected is on the order of a couple millimeters per second of a totally unexplained component of Saturn's gravity field. So this, in the initial analysis by our collaborators, Luciano Yes and Daniele Durante, who are working out of Rome, they were able to account for this using a variety of models. For example, one of the nominal model they used was stochastic. So they just said, okay, you have random accelerations. We're just going to take whichever acceleration set of accelerations we need in order to reduce the residuals of the data down to the noise level. Right. And then they just accounted for the error that introduced by using the synthetic model. And they also investigated the possibility that it was seismicity. So what is seismicity on giant planets? This is any body, for example, this teacup, will have a discrete set of normal modes such that when you strike it, it will ring with a set of frequencies. And the same is true for planets. And by measuring those sounds that the planet makes, essentially, you can learn about its interior properties. Okay, so that was all a lot of introduction, but that's the context of what we're doing. Okay. Right. So now we're investigating the possibility that the source of this gravity, of this sort of anomalous dark gravity, is seismicity. And if that is the case, we're going to see if we can constrain what modes might be responsible for it. Okay. Yep. So that's what we're trying to do here. Got it. Okay, and we find, surprisingly, that P modes in a relatively high frequency range are the most likely candidates to be responsible for the observed signal. Okay, so what is a P mode? A P mode is a pressure mode. So these are acoustic modes that have pressure as the restoring force. And these are in contrast to F modes, which are fundamental modes, which are a little bit more complicated. Okay, so let's maybe go to figure 1. Sorry, I've been talking nonstop. Do you have any?
No, you're good. If I see something I don't understand, I'll swing you. Okay, so figure 1, looks like we got some Eigen frequencies here, and boom, boom, boom.
Yes. So figure 1 here, I mentioned there's a discrete set of Eigen frequencies. And so this is just plotting what those Eigen frequencies are. So it has this characteristic ladder structure that might be familiar from quantum mechanics. It's just a general feature of the way that these harmonics work. Yep. So what are we plotting here? On the x-axis, we have L, which corresponds to what is called the degree of the mode, and this just has to do with the spatial scale of the mode. So these are all just spherical harmonics, and a low L or a low degree mode will have a very large spatial structure. So there will be so for example, the L equals 2 mode that's zonally symmetric will have like a blob on the top and bottom that are symmetric, and then like a band around the middle.
So it's a dipole.
Sorry?
It's a dipole.
Yes, exactly.
L equal 2 is a dipole, L equal 4 would be a quadrupole.
Yes, exactly. Right. And so, so on the x-axis, we're measuring the spatial scale of the mode decreasing to the right. So the spatial scale gets smaller as you decrease to the right.
Right.
The y-axis is just the frequency of those modes. Each of these different colors of curves corresponds to different radial order. I don't think in this paper I have a figure that shows what these eigenfunctions look like, but the idea is similar to imagining a guitar string. So a guitar string has the fundamental mode where the whole thing is oscillating, and then it has these higher harmonics where you have nodes in the middle. So that's essentially the same thing that's happening. And these higher harmonics will have higher frequencies. And you'll notice that there's some fine splitting between them. That's because there's a difference between the zonally symmetric modes, the prograde modes, and the retrograde modes. Their eigenfrequencies are offset because of the Coriolis force. So that's what causes the fine splitting. This is most important for the low frequency F modes, but it's less important for the P modes. Okay, so I'm saying F modes and P modes. What do I mean by that? This blue curve, the bottom one here, are the lowest frequency fundamental modes, and those are the F modes that we are saying are not likely to be the dominant contributors to the gravity field perturbations. And all of those higher modes that are higher frequencies, or not all of them, actually there's a particular preferred range of frequency space, but it's those modes that appear to be the ones that are most likely to reproduce the observed signal. So,
yes. And
let's see.
You do mean megahertz there, or what do you mean millihertz? Millihertz on the y-axis.
Yes, millihertz. Okay. So
good.
these are low frequency infrasonic sound waves. You wouldn't be able to hear them, but they are still sound waves. Right. And these are just standing waves that exist in the interior of the planet. Okay, so here we have a similar diagram that uses the same color convention. And the difference here is that on the y-axis, we have the delta C, which is just the notation that means the perturbation coefficient to the gravity field. So essentially, the bigger this number is, the larger the perturbation is. And it's all scaled to a 1 meter surface displacement.
Okay.
So what you see is that if you have a 1 meter surface displacement for all modes, then you would expect the F modes to dominate the signal. Yep. I didn't put a eigenfunction plot, but the idea is that the gravity field is going to sum over the density perturbations over the whole planet. And for the fundamental mode, you have no nodes. So it's just kind of, there's an open boundary condition. So it's just one perturbation all in the same direction. Whereas these P modes, these higher order modes, are going to have nodes in the middle. And that means part of their eigenfunction is going to be negative and part of it is going to be positive. These two effects will interfere destructively so that the total gravity field perturbation is going to be smaller by orders of magnitude.
So I think in order to calculate these eigen frequencies and eigenfunctions, you need to know a little bit about the structure of the object. So at this point, where is the structure coming from? Is this from a model? Is this from observations of Cassini, of density and temperature with respect to depth, or where is this coming from?
Yeah, so we're using an approximation for Saturn's interior structure that we know from observations is not exactly correct, but it's good enough for our purposes. And so we're approximating the interior to be an n=1 polytropic model. Yeah, and when you can run this through software that actually is based on your software, Mesa. It's but it's built on top of it. It's called Gyre Stellar Oscillation Code.
Yes.
I was actually just looking, and I saw that the newer versions of Mesa include stellar oscillation functionality. Is that true?
That is true. That's been in there for at least, I think, the last 2 or 3 public releases. So normally you would run Mesa to get your model, stellar model or planetary model, as the case may be. And then you would feed those structures into Gyre, which would then calculate your eigen frequencies, eigen functions, etc. But there is a mode where you can call Gyre directly within Mesa as it runs. And the advantage of this is that it allows you then to investigate things dynamically. There's also a lot less file motion going along because it's 2 programs talking to each other directly. And so it is very convenient if you're going to be doing a lot of this.
Great. Yeah, well, I suppose thank you for making this possible then. So yeah, and when you calculate these displacement eigenfunctions, you can just use the continuity equation to derive the density perturbations, and then you just integrate over space like you learn in freshman physics, and that's how you calculate these values.
Got it. Cool.
And so this plot is essentially meant to convey that a priori, if you have equipartition or of energy between the modes, or if you have the same amplitude for each of the modes, then you would expect the F modes to dominate the gravity signal. Right. And so if the P modes were to dominate the gravity signal, hint, hint, it would mean that there must be some strong frequency dependence or some other quantum number dependence in order for them to be the dominant component of the gravity signal. So it's a somewhat surprising result that I'm sort of getting a little bit ahead of.
All good. All good. Okay.
So I think at this point, I want to skip to figure 6, if that is possible.
Sure, nonlinear is great.
And for now, just focus on the red dots. Don't focus on the black curves, but we'll come back to where the black curves come from.
Okay.
But this is the input data we have essentially. So if you take the velocity signal that was received from Earth from Cassini, and you subtract all of the effects you know about. These include radiation from the sun, intrinsic radiation from the planet, perturbations from the rings, like the static gravity field of the planet, from gas drag from the small amounts of gas that exist even far up above the atmosphere, because you actually are just a few thousand miles above the cloud tops, and satellites. You factor in everything you can think about, and usually when you do this, you're able to get the residuals to be at the noise level. But this time, the residuals are significantly outside of the noise level. You can sort of by eye tell what the noise level is, and you can see that there exists a coherent structure that's not randomly stochastic,
right.
that is unexplained. And the difficulty with trying to explain this with seismology is that even if you were able to know a priori what the what the spectrum of the seismicity was. So you go through all the modes, and you are you know, instructed by some cosmic force as to what exactly these amplitudes are. You still are not actually able to deterministically predict how that's going to affect the gravity signal. The reason why is just that each of these modes have different eigenfrequencies, and for that reason, even if they are coherent over long timescales, meaning if you know the phase at one time, you can predict what the phase is going to be in a future time, we don't actually know the eigenfrequencies very specifically because we don't have a perfect understanding of Saturn's interior structure. And so even if you're only wrong by a tiny amount, say like 0.1% in your modeling of what these eigenfrequencies are, it's still going to be an effectively random phase for each flyby, because the timescale between each of these Cassini flybys is weeks. So even if it's only a small error, you're going through so many periods that you basically have no information about what the phase of each mode is going in. And so for that reason, there's this stochastic aspect to the problem that makes it difficult to do a good forward model calculation that doesn't have an impossibly large number of free parameters.
Yes.
So this is the problem we're faced with, and the resolution that we came up with is to stack the data, which is a common technique in various fields of astronomy. It hasn't been done in quite this way before, but the idea is that if you take the root mean squared, if you square each of these velocity displacements and then average them together, if you have an infinite number of them, then they will converge onto some deterministic prescribed behavior. Yep. And so in that way, you can do a forward model that can make a deterministic prediction.
Okay.
So then I want to show figure 5, which is essentially showing what that looks like. So again, ignore the black curve for now, just focus on the red data points. So when you average all of those together, you get something. We still have you get something that has, you know, a characteristic shape. You can see in the red data points, ignoring the black curve for now, just the red data points have a you know, a characteristic shape that looks like it's doing something. So unfortunately, we didn't have an infinite number of flybys. We only had 5. So there still exists quite a bit of stochasticity in the problem. But what you can do is you can take forward models and you can say, okay, if the spectrum is this input spectrum, you can calculate the probability that it would reproduce the data that has been observed within some tolerance threshold. And so this is useful sort of in the Bayesian sense. So you can in sort of Bayes' theorem, there's the aspect in the numerator of what is the probability of the data given the model, given a particular model. And so what this analysis allows you to do is update your priors about what you expect the spectrum to be. So for example, your prior expectation might be that F mode should dominate the gravity signal, but you should update these priors based on this work. The results that I will now show, which are from figure 3. Sorry, I'm jumping around so much.
It's all good. Your story's coherent. That's good. Okay, figure 3. Let's decrease that just a tad. There we go.
All right. So what we ended up using is a simple Gaussian dependence of energy on frequency. So we tried a variety of things. We thought about power laws, we thought about broken power laws, we thought about explicit dependence on quantum numbers rather than dependence on frequencies. And none of those worked as well as a simple Gaussian model for the dependence. So here on the x-axis, you have the peak frequency, so where the Gaussian is centered, and then, oh, sorry, on the y-axis is the peak frequency. Sorry about that.
Sorry,
and then on the x-axis is the width of the Gaussian, and it's kind of a convenient thing to use So we're not actually trying to claim that the distribution of these frequencies is actually Gaussian. But by parameterizing it this way, we're able to do two useful things. First of all, we're able to take a problem that in principle has an infinite number of degrees of freedom and release it down and reduce it down to 2 degrees of freedom, so that we're not overfitting the data. We're actually just trying to tease out the intrinsic properties of the data. And by that I mean you end up finding which frequencies dominate, and you end up finding how tightly clustered it is. Like it is, are all the modes, you know, contributing a small amount, or is it really a pretty small number of modes that are dominating the signal? And you're able to sort of probe for these broad features using only 2 parameters. The other thing that's nice about it is that if you use a very large width for your Gaussian, then you can have it sort of approximate exponential behavior or exponential decay, depending on where you put the center of your Gaussian.
Right.
And so you're really able to probe for a large variety of possible possible frequency dependencies using a relatively simple function. So what we find is on the left here, you have a coarse-grained grid search, just to try to find the general area that is preferred, or if there is a preferred area at all. And then on the right, you have a finer grained grid search to see if you can really nail down any specifics. And what we find is that you can't. The stochasticity is such that there are a variety of models that exist that have a finite probability of reproducing the observed data. But there does appear to be the models that work appear to have something in common, and the highest probability models do tend to cluster in this region of parameter space, roughly between 500 and 700 microhertz, where their function is peaked, and with relatively narrow bands. So it doesn't look like it's this broad thing where like tons and tons of modes are contributing. It looks like there might be a preferred frequency, and it looks like it might be in this range. But as you see, just because that's the darkest part of the distribution, there are other possibilities that are that cannot be excluded because they have a finite probability of reproducing the data within our error tolerance. So another way to visualize this is shown on figure 4.
Yes.
And this just plots up what those Gaussians look like. So the opacity of each of these corresponds to the probability that if this were indeed the frequency, the dependence of mode energy on frequency, then what is the probability that you would reproduce the data within the error tolerance? And what you can see is that there appears to be a cluster. And even though it's degenerate, and even though some of these are sort of outside of the most opaque cluster, there's a lot of overlap with the ones that are outside and the ones that are in that most opaque region. And so this sort of gives us a cautious view that maybe the data is trying to tell us that this is the region of frequencies that are the most dominant. And you know, because we sort of have this contrived idea that it's going to be a perfect Gaussian dependence of energy on frequency, it's likely that none of these models are exactly correct, but it seems to be indicating that this frequency range is the preferred region that reproduces the data.
Cool.
And so now figure 5 and 6, if you look at the black curves, these just show how our model does. So when you stack the data, this black curve shows how well, you know, one of our better fit models does. This is just an example, but this is with a peak frequency at 600 microhertz and a width of 40 microhertz. This is roughly what you get. It looks pretty good. There are a few problems. For example, very near closest approach, the black curve is doing these wiggles that do not appear to be happening in the data. So there are a variety of things that could be happening here. One of them that we've thought about is the possibility that signal from the normal modes may actually be larger than the data that's being presented, because the pipeline that produced this residuals data had the optimization that it was trying to reduce the residuals as much as possible.
Yeah.
So if there were higher frequency content, that could be aliased into higher order J's.
Okay.
So that's one reason why this might work, why that sort of disagreement might be happening. Or it could be something else. Another possibility, of course, is that this entire gravity signal is not due to seismicity at all. That was an assumption we made, but there are other possibilities. It could be convective anomalies. It could be a really complicated non-zonal structure, although that is sort of disfavored because it doesn't seem to converge on a low order solution the way you might expect it to. It's like every flyby you add to the data set necessitates adding more parameters and more and more of these sort of like higher order non-zonal structures. But we can't rule it out. It could be that it is some higher order non-zonal structure.
But just off the top of your head, I don't mean to put you on the spot, but if you when you take your atmosphere model of Saturn, and it's presumably convecting on the outside,
mm-hmm.
What is the rough turnover time? What is the convective turnover time out there? I'm just trying to see if that's large or small relative to the flyby period. Is it weeks? Is it hours?
I think it's like 10 centimeters per second up, roughly, and then the scale height is like 20 kilometers. So
okay. There you go.
Some math.
I can take it from there. That's good. That's the two numbers to go with. Okay, very good.
So yeah, it probably wouldn't be the equilibrium convection that would be occurring in the atmosphere. It would probably have to be something with more coherent structure that's like happening deeper down. But this isn't my topic or my area of expertise.
We're
getting out of my
off target here. Okay, so let's go to figure 6 then. Now that we got the black curves up there.
Yes. So figure 6 just shows that using this same technique, you're able to also do a decent job at reproducing the individual flybys. So these were just obtained by using the same input spectrum as in the previous figure. This is just an example. There are others, that work just as well within that degeneracy area. Some of them have less of this wiggly behavior. This 600 microhertz is kind of on the higher end. But
right.
Anyway, you're able to reproduce the general behavior of what's going on. Like you have this little dip here. You're able to. I spent a lot of time getting my hands dirty with the data, but what you find is like getting this slope to be right and getting this like plateau to be right is not something that can be reproduced very very easily. You need particular frequencies and spatial structure of the modes in order to reproduce this. And the fact that this is the same amplitude spectrum for each of these. So the only difference between these is the stochasticity and the phase. And they're able to do, I think, a pretty good job at getting this data a lot closer down to the noise level, so that they would be residuals that you can that would be within what is normally considered tolerable for these types of experiments. So I think that if this is indeed a result of seismicity and not some other effect, then the data seems to indicate that P modes are favored to produce the structure that we observe in the data. And finally, I want to go to table 1, which just shows, again, for that same sample, we're just trying to be consistent, but I want to emphasize that this is not the only possible solution. It's just one of a degenerate set that bears some similarities. We list the amplitudes just for this example that the modes would have in the above 2 examples with the black curve going through the data. And what you find is that the amplitudes of the modes would need to be of order kilometers in order to cause the perturbation that's that large. So for a little bit of context in the field, there were observations on from Earth on Jupiter that saw amplitudes that were more on the order of 50 meters. And those are already considered to be larger than can be accounted for based on the excitation theory that we have for the sun. So that was already a surprising result. And these are an order of magnitude larger. So those ones are like, of order 50 to 100 meters, and these are of order 1,000 meters. So,
Yep.
so that's a full order of magnitude. Okay, so what does this mean? I mentioned before that this study should be thought of in the Bayesian sense, in that these are updating our priors. And I think that there are fairly good reasons to think that to have a prior assumption that the amplitudes of these modes should not be that large, based on our current understanding of how these modes are excited. But nevertheless, here appears to be an indication by data that this model is indeed favored. So what does that mean for the future? I think that this is a very falsifiable prediction that we're making. The amplitudes are so large that they should be able to be detected with Earth-based telescopes. So if you, for example, use a Doppler imager and take a time series of the map of Saturn during equinox, when its rings are not in the way, and with something like a meter or 2 meter telescope, you need continuous observation. So it would need to be either in some Arctic latitudes, or have a sort of global network with a reasonable duty cycle. But it should, we have the technology to test whether or not this sort of this indication, this from the data from Cassini can actually be corroborated or falsified. This is something we can do from Earth. We don't have to send another mission. I think that's probably worth doing to either humiliate me, or to
or lionize. I don't know.
Yeah, or I'll be seen as a great predictor or whatever. But that's the process of science. I also want to mention that there is reason in my mind to think that strongly peaked frequency dependence in modes is not physically unreasonable. So the reason, from what we know about excitation of solar acoustic P modes, is that it's likely to be caused by the vigorous convection in the envelope.
Yep.
And the reason that this doesn't work for the giant planets is that if you use the same equilibrium model, or quasi-convective equilibrium model, the velocities are just not sufficient, because really what matters is the Mach number of these velocities. And in the sun, they're very close to the speed of sound, and therefore very efficient at exciting acoustic waves, in the same way that helicopters whose blades are going near the speed of sound are very efficient at. Anyone who lives in LA will know what I mean. But in that case, there's the same strong frequency dependence, where the characteristic turnover timescale of these eddies is commensurate with a strongly peaked amplitude that's observable from Earth-based observations. And this is not true of the turnover timescale of the modes on the giant planets. It's a lower frequency in that case, but planets are more complicated than stars, because they have condensing species. And so one example that we've sort of tossed around is the idea that you might have some meteorological activity that has a turnover timescale that might be commensurate with this. And if that were the case, then it could be argued that you would expect a strongly peaked frequency dependence that has to do with the characteristic turnover timescale of these storms, these cumulus storms. So that's one possibility. Okay, I think that's all I have to say.
Oh, very good. No, it's interesting, thought-provoking that they may not be excited by convection, but stuff even further up in the atmosphere through climate and weather, storms. Interesting, very cool. Well, I think there's a lot to do in this field still. So when is the next time Saturn goes edge on? I don't know that off the top of my head.
I don't know. I can Google it, but I'm not exactly sure.
Yeah. Well, in your lifetime.
The orbital period of Saturn, fortunately, unlike the orbital period of Neptune or Pluto, is such that you can wait over human timescales for the optimum configuration.
Awesome piece of work. Awesome piece of work.
Yeah, thank you so much for reaching out.
Yeah, well, Steve, thank you so much for spending some time and walking us through your paper.
Right.
All right. We'll see you, everyone. Bye-bye.
Bye.